Welcome to TechXBytes. In this tutorial, we will learn how to use Pandas, a powerful data manipulation and analysis library for Python. Pandas provides easy-to-use data structures and methods designed for working with structured data. Whether you're analyzing financial data, processing CSV files, or preparing data for machine learning, Pandas is an essential tool. By the end of this tutorial, you'll understand how to load, manipulate, analyze, and visualize data using Pandas. Let's get started on your journey from zero to hero. Before we begin, it's best practice to create a virtual environment for our project. A virtual environment is a self-contained directory that contains its own Python interpreter and packages, keeping your project dependencies isolated from your global Python installation. This prevents version conflicts between different projects. Once your virtual environment is set up, the next step is to activate it. This step is important because it ensures that any Python packages you install or scripts you run will use the Python interpreter and dependencies isolated within the environment rather than affecting your system-wide setup. On Unix-based systems like macOS or Linux, you can activate it using the source command followed by the path to the activate script. On Windows, simply run the path to the activate script without using source. With our virtual environment active, we can now install Pandas and related libraries. We'll install Pandas for data manipulation, Matplotlib and Seaborn for data visualization, and OpenPixel to work with Excel files. Pip is Python's package installer, which will download and install these packages from the Python package index. The first step in using Pandas is to import the library. We use the statement import pandas as PD, whereas PD creates an alias. This allows us to refer to Pandas simply as PD in our code, which is a widely adopted convention among data scientists. Using this standard alias makes our code more readable and consistent with examples you'll find online. Think of this as giving Pandas a nickname to make it easier to call upon its methodology throughout our code. Along with Pandas, we're importing two visualization libraries. Matplotlib is a comprehensive library for creating static, animated, and interactive visualizations in Python. We import its plotting module as PLT, which is the standard convention. Seaborn is a statistical data visualization library based on Matplotlib that provides a high-level interface for drawing attractive statistical graphics. We import it as SNS, named after the founder of statistical graphics, John Snow. These libraries will help us visualize our data analysis results in various formats like line charts, bar graphs, histograms, and more. The first step in creating a data frame is preparing the data. Here, we're using a Python dictionary where each key represents a column name and each value is a list containing the data for that column. This dictionary structure is perfect for converting to a data frame because it naturally maps to the tabular format we want. All the lists must be the same length since each list item will become a cell in a row. This approach is especially useful when you have data already organized in Python data structures, or when creating sample data for testing and demonstrations. Now we convert our dictionary into a Pandas data frame using the PD, data frame, constructor. A data frame is the primary data structure in Pandas. It's a two-dimensional, size-mutable, potentially heterogeneous tabular data structure with labeled axes, rows, and columns. Think of it as similar to a spreadsheet or SQL table. The constructor automatically assigns integer indices, starting from 0 to each row, and uses the dictionary keys as column names. This simple line of code transforms our raw data into a powerful data structure that provides numerous methods for data manipulation, analysis, and visualization. To view our data frame, we simply use Python's print method. Now, as you can see, when we run this Python code to print the data frame, it displays the data in a clear tabular format. Let's begin with the most common data format, which is CSV, separated values. Pandas provides a simple way to read it using the read CSV method. When you provide just the file name, Pandas assumes the data is separated by commas and that the first row contains the column headers. This works well for most standard CSV files. Even though Pandas assumes commas by default, it's a good habit to specify the delimiter yourself. This is especially important when working with data that might use tabs, semicolons, or other characters to separate values. Now let's look at how to tell Pandas which row contains the column headers. Sometimes, the first row of a file doesn't actually contain the column names. With the header option, you can tell Pandas exactly which row to use. Setting it to 0 means the first row contains the headers, while setting it to none tells Pandas that there are no headers, and it should create generic column labels like 0, 1, 2, and so on. Now, what if you want to assign different data types to different columns while reading the file? By default, Pandas tries to guess what kind of data is in each column, but sometimes it gets it wrong. You can make your code clearer and safer by specifying the data types explicitly when reading the file. For example, here name and city are treated as text. Age is set as a small integer type, and salary uses a 32-bit floating point. This not only ensures your data is read correctly, but can also save memory, because Pandas' default types are more generic and often use more memory than necessary. By knowing your data's limits upfront, you can choose more efficient types and improve performance. For instance, in our example we used int 8 for age because ages are always less than 100, so an 8-bit integer is enough to store the values. Now let's take it one step further and see how we can apply custom transformations to the values as they are read. Sometimes, your data might have little inconsistencies, like names with extra spaces or mixed casing. Pandas lets you clean up these values right as you load the file using the Converters option. Here, we're trimming spaces and converting the name column to lowercase. This makes your data cleaner and more consistent without needing a separate step later. Now that you've seen how flexible reading CSV files can be, let's move on to Excel files. Just like with CSV files, Pandas can read Excel files with a single line of code. If you don't specify a sheet name, it will load the first sheet by default. This is handy for simple files that only contain one table. Excel files often contain multiple sheets. Using the sheet name parameter, you can tell Pandas exactly which one to read. In this example, we're loading the sheet named 2024 Sales. Next, just like with CSV files, you can control which row should be used as the header. If your Excel file has titles or notes before the actual column headers, you can skip past those and tell Pandas where the real headers begin. Just set the header row to the correct index. And similar to CSV files, you can set expected types when reading from Excel. This helps make sure columns like salary are treated as numbers instead of text, and that text fields don't accidentally mix with numbers. Now let's look at another format that's very common for web data, JSON. JSON files are used a lot in web applications and APIs. With Pandas, you can load them just like a CSV, just provide the file name, and it will parse the structure for you. Now let's move to HTML files, where data often lives in table tags inside web pages. When data is stored in HTML tables, like on a web report, their Pandas can help extract those tables using read HTML. Since there could be more than one table on the page, Pandas returns a list, and you can pick the one you want, usually by index. Next, let's see how to connect to a SQL database and pull data directly from there. If your data lives in a database, Pandas can connect directly and run queries using SQL. You just write your query, pass in the database connection, and it pulls the results into a data frame. This is ideal for handling large or live datasets in professional environments. As you've seen, Pandas can read data from a wide variety of formats like CSV, Excel, JSON, HTML, SQL, and more like Parquet and Feather, which are optimized for speed and efficiency. While the file types are different, the process stays remarkably consistent, one line of code, and your data is ready to use. Let's move on to downloading a sample dataset to work with. Now that we have a good understanding of how to read data from various formats, let's download a sample dataset containing sales data. This dataset will be used for the rest of the tutorial to demonstrate various data manipulation and analysis techniques. Now that we have our sample dataset, we can load it into a Pandas data frame using the read CSV method like we discussed earlier. Here, we're also using a converter to ensure that the date column is read as a DataTime object. The error equals coerce parameter in the pd.toDataTime method ensures that any invalid parsing will be set as NaT, not a time, which is useful for handling inconsistent or malformed date entries in your dataset. This is important for any time-based analysis we might want to do later. Let's start by looking at the columns in the data frame. Using columns, TOList gives us a list of all column names. This is a quick way to understand what kind of data we have. Here we run the Python script that prints the list of column names. You can see all the columns loaded from the dataset displayed in the terminal. The info method provides a concise summary of the data frame. It shows the number of entries, columns, non-null counts, and data types, plus the memory usage. This helps us spot missing values and understand the data better. Running the info log script prints this summary to the terminal. It gives you a clear snapshot of your dataset structure, including how many values are missing in each column. The describe method gives you useful statistics about the numerical columns. It shows counts, averages, standard deviations, min, max, and percentile values. This helps you quickly understand your data's distribution and range. When you run this script, it prints a summary of statistics for the numerical data, letting you check for outliers, data spread, and central tendencies. Using head without parameters shows the first 5 rows of the data frame. This helps you quickly check what your data looks like at the start. Running the head log script displays the first 5 rows in the terminal, giving you a glimpse of the actual data your data frame contains. You can also pass a number to head to see the first n rows. By default, it shows 5 rows, but you can customize this to fit your needs. For example, we are passing 3 to see the first 3 rows. Running this script will print the first 3 rows to the terminal, useful when you only want a smaller sample of your data. The tail method shows the last 5 rows by default. This is useful for checking the end of your dataset. Running the tail log script outputs the last 5 rows in the terminal, so you can see how your data finishes. Like head, you can pass a number to tail to see the last n rows. For example, we are passing 4 to see the last 4 rows. Running this script will print the last 4 rows to the terminal. This is useful for verifying that the data was loaded completely and for seeing the most recent entries in time series datasets. There are 2 main ways to access columns in a data frame. The first method uses dictionary-like indexing with square brackets, where you pass the column name as a string inside the brackets. The second method uses attribute-like access with a dot notation, which is more concise, but only works if the column name doesn't have spaces or special characters and doesn't conflict with data frame method names. Both methods return a Pandas series object, which is a one-dimensional labeled array. Accessing columns is fundamental for data analysis, as it allows you to focus on specific variables or features in your dataset. Now to see how series objects look, let's run the script that prints the category column as a series. The output shows the values in the product column as a Pandas series. Each row is indexed, and the value for each index is displayed. This is useful for quickly checking the contents of a specific column. To select multiple columns from a data frame, we use dictionary-like indexing with a list of column names. Notice the double square brackets. The outer brackets are for data frame indexing, and the inner brackets create a list of column names to select. This returns a new data frame containing only the specified columns, maintaining the original row order. This technique is useful when you want to focus on a subset of variables for analysis or visualization, or when you need to create a more manageable dataset with only relevant features. The output shows the values in the product and category columns as a Pandas data frame. Each row is indexed, and the values for each index are displayed. This is useful for quickly checking the contents of multiple columns. The ILOC indexer is used to select rows by their integer position index location. The first example selects the very first row index 0 of the data frame, returning it as a series. The second example uses slicing to select the first 3 rows, indices 0, 1, and 2, returning them as a new data frame. Note that slicing with ILOC follows Python's standard slicing rules where the end index is exclusive. This method is particularly useful when you know the exact position of the data you want to access, regardless of the actual index values assigned to the rows. The output shows the first row as a Pandas series and the first 3 rows as a Pandas data frame. Now let's see how to select rows based on their labels instead of their positions. The lock indexer is used to select rows by their labels. For this to work effectively, we first set a meaningful column, in this case, name, as the index using setIndex method. This creates a new data frame where the name column becomes the index. Then, we can use lock to select a specific row by its label, e.g., John, or multiple rows using a list of labels. Lock is powerful because it allows you to select data based on meaningful identifiers rather than positions, which is often more intuitive and less error-prone, especially when your data changes. The output displays data for the smartphone product as a Pandas data frame. Each row is indexed by the product name, allowing for easy lookup, and the corresponding values for each product are shown. This makes it convenient to inspect multiple rows based on their labels. Now, let's take it a step further and explore some advanced selection techniques. Try experimenting with these on your own in the terminal to deepen your understanding. So, let's move on to the next topic, conditional selection. Conditional selection is a powerful feature that allows you to filter data based on specified conditions. Inside the square brackets, we provide a Boolean expression that evaluates to true or false for each row. Only rows where the expression is true are included in the result. The first example selects rows where the date column's month is February. The second example uses multiple conditions combined with the and operator to select rows where the category is electronics, and the price is greater than 100. This method is essential for data analysis, as it enables you to focus on specific subsets of your data that meet certain criteria. Similarly, you can use other logical operators like or and not to create more complex conditions. Next, we will work with the data frame to add new columns and rename existing ones. Adding new columns to a data frame is straightforward. You can assign values directly to a new column name using the dictionary-like syntax. If the column name doesn't exist, Pandas creates a new column. In the first example, we add a simple column with a list of values. But this will not work in our case since the length of the list does not match the number of rows in the data frame. In the second example, we use PD, series, to create a new column with specific index alignment. This is useful when you want to ensure that the new column aligns correctly with existing data, especially when dealing with larger datasets. So, in second example, the first 3 rows will be assigned the values 0.1, 0.2, and 0.15 respectively, while the rest will be none, which is the default value for missing data in Pandas. To make sure we have same value for all rows, we can assign a single value to the new column. In the first example, we set a default discount of 0.1 for all products. In the second example, we use the apply method to assign different discount values based on the product category. This is a powerful way to create new columns based on existing data. Finally, we calculate a new column called discounted price by applying a formula that uses the existing price and discount columns. This demonstrates how you can perform calculations and create derived columns in a data frame. Now, let's look at how the output looks like. The output shows the new discount and discounted price columns added to the data frame. The discount column contains the discount percentage for each product, and the discounted price column shows the price after applying the discount. This is a great way to enhance your dataset with additional information that can be useful for analysis or reporting. Now, let's move on to renaming columns. Renaming columns is a common task when preparing data for analysis. The rename method allows you to change the names of one or more columns. You pass a dictionary where the keys are the current column names and the values are the new names. The in-place equals true argument modifies the original data frame without creating a copy. This is useful for making your data frame more readable or aligning it with naming conventions in your analysis. Remember to be careful with renaming, as changing column names can affect downstream operations if other parts of your code rely on the original names. The output shows the data frame with the renamed columns. Each column now has a more descriptive name, making it easier to understand the data. This is especially helpful when sharing your data frame with others or when preparing it for visualization or reporting. Now, let's move on to data cleaning, which is a crucial step in data analysis. So, data cleaning is identifying missing values in your dataset. The isNull method returns a data frame of the same shape as the original, but with Boolean values, true where values are missing and false where values are present. When we chain the sum method, it counts the number of true values in each column, effectively giving us a count of missing values per column. This simple operation is crucial for understanding the completeness of your dataset before proceeding with analysis. High counts of missing values might indicate problems with data collection or processing that need to be addressed. The output shows the count of missing values in each column. In this case, the price column has 2 missing values, while quantity and revenue have 1 missing value each. This information is essential for deciding how to handle these missing values, whether by filling them in, dropping the rows, or using other imputation techniques. Now, let's see how to remove missing values. One approach to handling missing values is to remove the rows that contain them. The dropna method creates a new data frame that excludes rows with any missing values. This method is appropriate when the missing data represents a small portion of your dataset, and removing these rows won't introduce bias or significantly reduce the dataset size. However, be cautious with this approach, as it can lead to loss of valuable information, especially if many rows contain missing values. Always consider the context of your data and the potential implications of removing rows before deciding on this method. In some cases, it may be better to impute missing values rather than dropping them. Let's explore that next. An alternative to removing rows with missing values is to replace or impute them with meaningful values. The fillna method allows you to specify different fill values for different columns. Here, we fill missing values in the revenue column with the mean of that column, which is a common practice for numerical data. For the quantity column, we fill missing values with 0, which might make sense in the context of sales data. This approach helps maintain the size of your dataset and can be more informative than simply dropping rows. However, be cautious with imputation, as it can introduce bias if not done carefully. Always consider the context and implications of filling missing values in your analysis. Sorting is a fundamental operation for organizing data. The sort values method allows you to sort a data frame by one or more columns. In the first example, we sort the data frame by the date column in ascending order. In the second example, we sort by both date and revenue, where date is sorted in ascending order and revenue in descending order. This is useful for organizing data for reporting or analysis, as it allows you to quickly identify trends or outliers. Sorting can also be combined with other operations, such as filtering or grouping, to create more complex data views, which we'll be exploring next. Grouping and aggregation are powerful techniques for summarizing data. The groupby method splits the data into groups based on one or more columns, and the AG method applies specified methods to each group. Here, we group the data by the date column, converted to monthly periods, and calculate the mean revenue, mean and maximum price, and count of quantities sold for each month. This allows us to analyze trends over time and understand how different products perform in different periods. Grouping and aggregation are essential for generating summary statistics, creating reports, and preparing data for visualization. The output shows the grouped data frame based on the date column, with the mean revenue, mean and maximum price, and count of quantities sold for each month. This summary provides valuable insights into the performance of products over time, allowing for better decision-making and analysis. Now, let's move on to pivot tables, which are another powerful tool for data analysis. Pivot tables are a powerful way to summarize and analyze data. The pivot table method allows you to create a new data frame that summarizes data based on specified index and column values. In this example, we create a pivot table that shows the total revenue for each category by month. The agfunc parameter specifies the aggregation method to use, in this case, sum. Pivot tables are particularly useful for generating cross-tabulations and multi-dimensional summaries of your data, making them ideal for reporting and analysis. Let's try to see how it looks in terminal. The pivot table shows the total revenue for each category by month. Each row represents a month, and each column represents a product category. The values in the table are the total revenue for that category in that month. This format makes it easy to compare performance across categories and identify trends over time. Pivot tables are a powerful tool for data analysis and reporting, allowing you to summarize complex datasets in a clear and concise manner. Also, the NaN values indicate that there were no sales for that category in that month or that the data was missing. In case you want them to be filled with 0, you can use the fillNA method that we discussed earlier. Now, let's move on to time series operations, which are essential for analyzing data that changes over time. Pandas excels at time series analysis with specialized data structures and methods. To create a time series, we need to convert the date column to a data time format, which we have already done. Then we can use the PD date range method to generate a range of dates. The dates variable will contain a range of 10 dates starting from 2022-0101 with a daily frequency. Let's see how it looks in terminal. The output shows the generated date range as a DataTime index object, which is a special type of index in Pandas designed for handling time series data. Each date is displayed along with its frequency, which in this case is daily. This format is useful for time series analysis, as it allows you to perform various operations like resampling, shifting, and rolling calculations easily. Now, let's move on to the next part of time series operations. In this example, we create a time series using the generated date range as the index. The PD series constructor takes a range of values, 0 to 9 in this case, as we've 10 periods, and assigns them to the corresponding dates. This creates a time series where each value is associated with a specific date. The output shows the time series with dates as the index and corresponding values from 0 to 9. This format is useful for time series analysis, as it allows you to perform various operations like resampling, shifting, and rolling calculations easily. Now, let's move on to the real deal of time series operations, which is resampling and shifting. Resampling is a powerful feature in time series analysis that allows you to change the frequency of your data. In this example, we resample the time series to a 2-day frequency using the resample method and apply the sum method to aggregate the values. This is useful for analyzing trends over different time intervals. The second part of the example demonstrates how to shift the time series by a specified number of periods using the shift method. This can be helpful for calculating differences or creating lagged features in your analysis. The output shows the resampled time series with a 2-day frequency, where each value represents the sum of the original values over that period. The second part of the output shows the shifted time series, where each value is shifted by 2 periods. The NaN values indicate that there are no corresponding values for those dates after shifting. This is useful for creating lagged features or calculating differences in time series analysis. Now, let's move on to data visualization, which is an essential part of data analysis. You must have noticed the frequency of the resampled data is 2 days while for the shifted data is daily. Well, I leave that for you to figure out. If you have any questions, feel free to ask in comments. Now, let's move on to merging data frames, which is a common operation in data analysis. Merging data frames is a common operation in data analysis, especially when you have related data spread across multiple data frames. The PD merge function allows you to combine 2 data frames based on a common column or index. In this example, we create another data frame with product discounts and merge it with the original sales data frame on the product column. The how parameter specifies the type of merge to perform inner, outer, left, or right. In this case, we use inner to keep only rows with matching values in both data frames, as we already have the discount column in the original data frame. We won't diving deep into types of joins here, but let me know if you want to learn more about it in the comments. So, let's see how the output looks like. The output shows the merged data frame, which contains data from both data frames based on the common product column. The merged data frame includes all columns from both data frames, allowing you to analyze and work with combined data easily. Merging is a powerful tool for combining related datasets and is essential for data analysis and reporting. Now, let's move on to data visualization, which is a crucial part of data analysis. Data visualization is a powerful way to communicate insights from your data. Next, we will explore how to create various types of plots using the Matplotlib and Seaborn libraries. Pandas integrates seamlessly with Matplotlib for visualization. The plot method is a convenient wrapper around Matplotlib's plotting functions. Here, we create a histogram of the age column to visualize its distribution. The kind equals hist parameter specifies that we want a histogram, and bins equals 10 determines the number of intervals into which the data is divided. We also add a title using the title parameter. After creating the plot, we use Matplotlib's plt xlabel and plt ilabel functions to add labels to the axes, making the visualization more informative. Finally, plt show displays the plot. Histograms are particularly useful for understanding the distribution of numerical data and identifying patterns such as central tendency and spread. The histogram we created shows the distribution of ages in our sample data frame. The x-axis represents the age intervals, bins, while the y-axis shows the frequency of occurrences within each interval. This visualization helps us understand how ages are distributed across the dataset, revealing patterns such as central tendency and spread. For example, we can see that most employees fall within a certain age range, which can be useful for demographic analysis or workforce planning. To create a bar chart, we first need to prepare the data by calculating the mean salary for each city. We use the GroupBy method followed by selecting the salary column and applying the mean function. This returns a series where the index contains city names and the values are average salaries. Next, we call the plot method on this series with kind equals bar to create a bar chart, which is ideal for comparing categorical data. We add a title to the chart, label both axes for clarity, and then display the plot with plt show. Bar charts are excellent for comparing values across different categories, in this case showing which cities have higher or lower average salaries. The bar chart we created shows the number of sales for each product category. The x-axis represents the product categories, while the y-axis shows the frequency of sales in each category. This visualization helps us quickly identify which categories are performing well and which ones may need attention. For example, we can see that electronics has the highest number of sales, while clothing has fewer sales. This information can be valuable for inventory management, marketing strategies, and understanding customer preferences. Next, let's explore how to create more advanced visualizations using Seaborn, a powerful library built on top of Matplotlib that provides a high-level interface for drawing attractive statistical graphics. Before creating visualizations with Seaborn, it's often helpful to set a consistent style. Seaborn provides several built-in themes that control the appearance of the plots. Here, we use SNS, set style equals white grid, to apply the white grid style, which adds grid lines on a white background. This creates a clean, professional look that's easy to read. Other available styles include dark grid, white, dark, and ticks. Setting a style affects all subsequent plots in your session and helps maintain visual consistency across your visualizations. Then next we create a bar plot using the SNS bar plot function, which is similar to the plot method in Pandas but offers more customization options. We specify the X and Y axes, the data source, and then add a title and axis labels. The PLT tight layout function adjusts the layout to prevent overlapping elements, ensuring that everything fits nicely within the figure. Finally, we display the plot with PLT show, which will pop up a window with the plot. This is the bar chart we created using Seaborn. It's similar to the one we created with Pandas, but Seaborn provides a more polished and visually appealing output. The grid lines and overall style make it easier to read and interpret the data. Next, let's explore how to create a pair plot, which is a powerful way to visualize relationships between multiple variables. A pair plot is a powerful way to visualize relationships between multiple variables simultaneously. The SNS pair plot function creates a grid of scatter plots showing all pairwise relationships between numeric variables in the data frame. Along the diagonal, it shows the distribution of each variable. The hue equals category parameter allows you to color the points based on a categorical variable, making it easier to identify patterns and clusters. Pair plots are particularly useful for exploratory data analysis, as they help you quickly identify correlations, trends, and potential outliers in your data. In this example, we create a pair plot for the price, quantity, and revenue columns. The diagonal KDE option specifies that we want to use kernel density estimation for the diagonal plots, which provides a smooth estimate of the distribution. The pair plot we created shows the relationships between the price, quantity, and revenue columns. Each scatter plot in the grid represents a pairwise relationship, while the diagonal plots show the distribution of each variable. This visualization helps us quickly identify correlations and trends between multiple variables, making it easier to understand the underlying patterns in our data. Pair plots are particularly useful for exploratory data analysis, as they provide a comprehensive view of relationships in your dataset. Now, let's move on to creating a correlation heat map, which is another powerful visualization for understanding relationships between variables. Correlation heat maps provide a visual representation of the correlation matrix between variables. First, we calculate the correlation coefficients between all numeric columns using df, select dtypes, include equals number, core. This filters out non-numeric columns and then computes the Pearson correlation coefficient for each pair of numeric variables. Next, we visualize this correlation matrix using SNS, heat map. The ANOT equals true parameter adds the correlation values to each cell, and CMAP equals coolwarm specifies a color scheme where blue represents negative correlations, red represents positive correlations, and the intensity of color indicates the strength of correlation. Finally, we add a title and display the plot. The correlation heat map we created shows the relationships between numeric variables in our dataset. The color intensity indicates the strength of the correlation, with blue representing negative correlations and red representing positive correlations. This visualization helps us quickly identify which variables are strongly correlated, which can be useful for feature selection in machine learning and understanding interdependencies in your data. For example, we can see that price and revenue have a strong positive correlation, indicating that as price increases, revenue tends to increase as well. Now, let's move on to exporting data to different formats, which is an essential step in data analysis for sharing results or integrating with other systems. After analyzing your data, you'll often need to export the results for sharing or further processing. Pandas provides the to-CSV method to export a data frame to a CSV, comma-separated values file. CSV is a simple, universal format that can be opened by many applications, including Excel, Google Sheets, and other data analysis tools. The index equals false parameter omits the data frame's index from the output, which is usually desirable unless the index contains meaningful information. CSV exports are useful for sharing data with colleagues who may not use Python, or for integrating with other systems that accept CSV inputs. Sometimes you need to export data to Excel format, which preserves more formatting and can store multiple sheets in a single file. Pandas to Excel method exports a data frame to an Excel file. The sheet name parameter specifies the name of the sheet in the Excel workbook. Like with CSV exports, we use index equals false to omit the data frame's index from the output. Excel exports are particularly useful when you need to share data with non-technical stakeholders who prefer Excel, or when you want to preserve formatting information that would be lost in a CSV file. For more complex Excel exports, you can use Excel Writer to create a multi-sheet workbook. This is useful when you have multiple related data frames that you want to store in a single file, each in its own sheet. The with statement ensures that the Excel file is properly closed after writing, even if an error occurs. Inside the block, we export the original data frame to a sheet named Employee Data and the city statistics to another sheet named City Statistics. This approach allows you to organize related data in a structured way, making it easier for recipients to navigate and understand the information. Multi-sheet workbooks are particularly useful for reporting, where you might want to present both raw data and various summaries or analyses derived from it. Congratulations! You've completed our Pandas Zero to Hero tutorial. You've learned how to create, load, and manipulate data frames, clean and transform data, perform aggregations and merges, visualize data, and export your results. Pandas is an incredibly powerful library that forms the backbone of data analysis in Python. The skills you've learned here will serve as a solid foundation for more advanced data science and machine learning tasks. Remember that the best way to master Pandas is through practice, so try applying these techniques to your own datasets. Happy data wrangling! Thank you for participating in this tutorial. We hope this tutorial was informative and helpful. Please leave a comment for questions or feedback, and like if it was helpful. We encourage you to explore the Pandas documentation and link for the documentation you can find in the description below. See you in the next tutorial.